So today I'm going to give my last two lectures. Probably some of you have done the calculation, which I did probably later than you did, which is to note that it took one lecture for me to do 10D. It took almost two lectures for me to do 8D. And I've already explained that things get much more complicated as we go down in dimensions. So depending on what kind of an exponential we're working with here, it could take me a lot of lectures to get through 6D and 4D. So what I'm going to do is actually focus on today going through a careful and pedagogical explanation of the things I want to tell you about 6 dimensions. And I'm going to take some of the things I was going to say about 4 dimensions and compress them into short anecdotes, which I will include in the 2 lectures today. Most of what I was going to say about 4 dimensions was different in character from what I'm saying in 6 dimensions, in that part of the point of this whole series of lectures is to go through sort of pedagogically what we understand, first of all, globally about the set of vacua in these higher dimensions, and second of all, to develop some of the tools so you can actually start working yourself to look at different kinds of string models from different kinds of compactifications. And from both of those 2 points of view, I think it's more worthwhile to really go through carefully what we can say in 6 dimensions, where I think we're beginning to get a good global picture of what's going on, where we can cleanly and clearly describe the tools needed to describe the models in 6 dimensions, and where, because of the strong constraints from anomalies, we have a lot of checks and cross-checks that allow us to really fit these pieces together into what is approaching a good global picture. In 4 dimensions, if you imagine fitting together the set of string solutions or string vacua in a puzzle, in 6 dimensions we kind of have perhaps a good part of the, you always start on the edges with a puzzle, where we've kind of got a good part of the outline and maybe some big piece in the middle. Whereas in 4D, we've managed to fit together some pieces like this into some little patches, but we don't know how many pieces we're missing. We're not sure what the big picture is, and we're not sure how to fit them together. So what was already going to be a little anecdotal in 4 dimensions, I'm going to compress into some anecdotal elaborations on what I talk about in 6 dimensions today and later today. Good. Let's see. What else did I want to say to start out with? OK, so what we started doing last time, just recapping, we finished describing 8 dimensions, where we have 2 dual descriptions of a set of string compactifications, which basically give us the same space of string vacua from 2 different points of view. And then we had a very limited set of constraints, which don't really tell us anything about the gauge group. So we have a big apparent swampland of things which you can try to rule out or incorporate into string theory, although it seems more likely that they're not string vacua. So last time, we started to talk about 6 dimensions, where the story gets more exciting because now we have matter. So we now have a matter multiplet which lives in an arbitrary representation of the gauge group. And as I outlined, we're going to start by talking about the global scope of what you can get by trying to constrain as much as possible the set of theories which are possible. And then we'll talk about these 3 constructions: intersecting brane models, heterotic, and F-theory in 6 dimensions, which will, in each case, add a little bit of complexity to what we've done in the last lecture with heterotic and F-theory. So we talked about anomaly cancellation, and this is pretty much where we were at the end of last lecture. I wrote down for you the general anomaly cancellation formula. Remember, the idea here is that there are T+1 B fields which mediate the Green-Schwarz mechanism. So instead of a simple factorization in terms of the anomaly polynomial being a product of 2 smaller polynomials, we have a sum over some index, alpha and beta, of anomaly polynomials indexed by alpha associated with the different T+1 B fields. So we have an inner product space of signature 1T given by an inner product matrix omega. We've got some normalization factors lambda. And we have in this anomaly polynomial now a factorization of the one-loop formal 8-form anomaly polynomial, much like what we did in 10 dimensions, into a product of 2 factors of this x contracted with omega. And as I said last time, a simple example of this is when there's 1 anti-self-dual and 1 self-dual tensor multiplet, In that case, omega is just the off-diagonal 0, 1, 1, 0. A can take this form after linear transformation. B is parameterized like this. And the 8-form anomaly polynomial really is a product of these two guys, because this inner product turns into a product of the first component and the second component. And then I told you that there is a further physical constraint needed to pull us down to a smaller set of possible solutions, or which there is another constraint which we know about, and we might as well use it because it constrains the set of possible theories further. And that is that the gauge kinetic terms have to be physical, and therefore the sign of j dot b, where j is the vector associated with the scalar fields in the tensor multiplets dotted into these b's, all have to be positive. So that's where we were last time. Now I'm going to show you the full anomaly conditions. Yes, question?
Are you saying that you can always put this polynomial into this factorized form? Or?
Absolutely not. If you can't, then the theory cannot have its anomalies canceled, and it is not a good theory.
Oh, okay.
So just like in Green-Schwarz in 10 dimensions, if you write down a general supergravity theory in 10 dimensions with n equals 1 supergravity in a general gauge group, you're going to have an anomaly polynomial coming from the hexagon diagrams. In general, it's not going to factorize into this y4 times x8 form that Green-Schwarz used to cancel the anomalies. That only happens for two special gauge groups, for SO32 and for E8 cross E8. Okay? And similarly, this anomaly 8 form will only factorize in special cases. So only when there is a solution to these equations can we find acceptable supergravity theories. So this is providing us with constraints on the set of possible consistent theories. And so the first thing I'm trying to do in 6 dimensions here is to explore that set of constraints, because that will give us a sense of how big our playing field is. Once we know what those constraints are, then we know that anything we get from string theory has to fit in the space bounded by those constraints. And this is why I say we're getting a good picture of of how the puzzle fits together in 6 dimensions, because we have at least part of the boundary of the puzzle. And that boundary is coming from these anomaly constraints plus this condition here. Yeah, good question. Other questions?
Yeah. Can you explain a little bit more what this J is?
Sure. So there are a bunch of tensor multiplets. There are T of them. Okay. Each one has an anti-self dual B field and a scalar field phi. So the B's, there are T plus 1 B's, and they transform under this SO1T. And J is a vector of norm 1. I didn't mention that, but you can normalize it to 1, which lives in this space. So it's essentially just a vector in this space R1 comma T. So it's a vector which is parameterizing some of the moduli of these theories. So just think of it as a bunch of moduli. It's a bunch of moduli which are parameterized by a vector in this R1 comma T space. And therefore, we can take its inner product, according to omega, with the A's and B's. And in particular, its inner product with the B's has to be positive. This is the kind of positivity constraint, in all the common. Correct. We want the kinetic terms of the gauge fields to have the right sign, because if they don't, then there will be a sort of tachyonic instability in momentum space. Right? There's a common theme to lots of different vacuum constructions, which is you have something which is like a tadpole, which has to be saturated, and you have a bunch of things which contribute generally positively to the tadpole, and you add them up, and you can't put more than enough stuff to saturate the tadpole. And then there are generally some positivity constraints coming from supersymmetry. And this is precisely a positivity constraint. The J dot B is precisely a positivity constraint coming from supersymmetry. And it's going to actually play an important role in constraining what theories we can have. Yes, Tom?
Does varying these parameters correspond to varying fields, physical fields in theory?
Yes, varying J corresponds to varying the Kähler moduli in these theories. Yeah, it's just a bunch of moduli. J is the moduli. B are fixed vectors which we have to find in order to solve the anomaly cancellation conditions. So if you have a gauge group, then you need to find the vector A and the vector B so that this equation is solved. So let me now write down the anomaly equations a little more explicitly, and then actually give you an example of a solution, because they're they look like a big mess, and if I just flashed them up there and then moved on, nobody would be able to parse anything based on that. So let me just try to deconstruct this, and we'll actually do an example, so you will see how this works out. Yeah? You can start having arbitrary what?
Arbitrary functions in the conjugate. Like superdimensional
Yes, we don't have that here. We'll see that in 4 dimensions. In 4 dimensions, we'll see a superpotential. I don't know about odd dimensions, but we don't see it here in supersymmetric theories. Well, the choice of, I'm focusing on the discrete pieces, the matter fields, their representations in the gauge group. These live in continuous moduli spaces. I mean, this is something I should emphasize. We had this 8D discussion where I was talking about the gauge groups you could get, but these are really, generically you have U1 to the 20, and then there are special points where you get special things like E8 cross E6 or something if you get a certain enhanced gauge symmetry. But these are all in the moduli, in a continuous moduli space. So there's a continuous moduli space of theories, but it's a finite dimensional moduli space. At any point in the moduli space, you can write down a Lagrangian around that point. I'm going to kind of go with Tom here. Choose some moduli. You can write down a Lagrangian there. There's a global structure to the moduli space, which is a global structure of the scalar fields. There's a separate, in some sense, a separate theory in the way Tom would describe it, described at each one of these points in moduli space, right? But you can explore the moduli space by just moving the scalar fields around. Here, it is a similar story. We're really looking at just the massless content of this theory, but there's nothing analogous to, say, the superpotential, which we'll see in 4 dimensions in this case.
Is there something like a
I don't think for the theories I'm talking about there is. We'll talk in 4-dimensional theories. It's more useful, perhaps, to use that kind of structure to characterize what's going on. Yes. Mm-hmm. In 6 dimensions? That's the question we're asking. That's the question I'm trying to ask right now. Is what are the constraints? So the only Lagrangian you can write down with n equals 1 supersymmetry is essentially, I guess, good. I didn't write down the Lagrangian. It's basically the same kind of thing we've been writing down before. It's the Einstein-Hilbert term plus there's B fields which have H-form curvatures. You get H squared, you get F squared terms. There are a bunch of different parameters which are the moduli. So in particular, this J is going to parameterize the gauge couplings of all the different gauge fields. Right? So there are a bunch of different apparent gauge couplings, but they're related to J dot B for each gauge field. So if you didn't worry about the quantum structure, you would just have a different gauge coupling for each gauge field. Because of the anomaly cancellation condition, there's a relationship between J dot B, which controls the gauge coupling, right? Because there's trace F squared in the Lagrangian. That's the gauge, one over the gauge coupling in front of that. That's controlled by J dot B, which is related by supersymmetry to these B guys appearing in the anomaly cancellation. So we're actually, through this mechanism, fixing the gauge couplings based on the anomaly cancellation. I mean, there's still degrees of freedom encoded in J, which are still a good moduli space. So that's all sort of forced on you by the supersymmetric structure of the theory.
question?
Yes?
So is there a theorem along the lines that if you can't cancel anomaly by Green-Schwartz mechanism, you can't do it any other way?
I would like to be able to say yes, but I think it is. Lots of people have tried hard to find out. Before Green and Schwartz found their mechanism, lots of people tried to. You can try to find various counter terms and things like that. I think that in 10 dimensions, you can pretty much exhaust the set of possible counter terms, and it becomes clear that there's no way to do it. I'm not sure that in 6 dimensions anyone has exhausted the space of possible counter terms, although I think a similar argument will probably go through. But I can't point to a paper I'm aware of where there's a definitive proof, unless Joe knows of one. Or, yeah. Tom?
Yeah, when you have multiple tensor multiplets, you could think of it as having the interacting formal field theory of those tensor multiplets and then being out on the moduli space.
Yes.
Is that point where they interact somehow included in this as a special point in moduli space?
So I think what you're talking about may be related to these tensionless string points. where those are included in this moduli space, but we don't have a low-energy Lagrangian description. So yeah, this is actually part of why I was hesitating in part of my responses to the previous questions. There are a bunch of six-dimensional supergravity theories which we can't describe by Lagrangians, but we seem to be able to get at them as limits of F theory. And in fact, they're the places where there are transitions between theories with different numbers of tensor multiplets. I wasn't going to go into this right now, but really this whole space is kind of a connected space with different pieces, each of which is a moduli space with a fixed number of tensor multiplets. And there are special points where we don't have a Lagrangian, but it seems like it's still a fine theory, and those are places where you can move through a transition from a theory with one number of tensor multiplets to another. And when we get to the F theory description at the end of the day today, we'll actually see very clearly how to describe that in F theory. So yeah, it's a very interesting story there. I was trying to move some of that to later. So let me try to deal with this big mess of equations for a minute so that we can kind of see what it's all about. And when we refer to these later, that won't just seem like a big mess. Yes? Alpha is an index in the R1 comma T space. That's an index which we always contract using this omega. I'll tell you what I is in a moment. Okay? I is just an index. Sorry, I is an index into the different. Good. So we factorize the gauge group. I've already told you what I is. We factorize the gauge group into G as a product of G1, G2 through GK. I is an index in that set, 1 through K. Yeah, sorry, I forgot. I already told you that. So this is basically, there's an implicit sum here. We're summing over all the gauge group components. There's a trace F squared, a normalization constant lambda, and a vector B. In each gauge group, there's a separate vector B. So we have one vector A associated with gravity, and K vectors B associated with the different components of the gauge group. Yeah, thanks for asking that, actually. I didn't mean to push you off on that. It's the X's I'm about to describe, which I thought you were asking about. Okay, any other questions? I think this will be clearer once I give you an example of this. So let me just first of all outline what these equations are, and then let me give you an example. So basically, just like in Green-Schwarz, we have, in Green-Schwarz in 10 dimensions, we have a bunch of square diagrams with either F's or R's coming out in a formal 8-form anomaly polynomial. And in order for that to factorize as a product, first of all, two things have to vanish. We can't have an R to the fourth, because if we have an R to the fourth, that's clearly not going to come from any kind of factorization, trace R to the fourth. You can't have a trace F to the fourth for the same reason. So those are two things which just have to vanish. So let's read those off. This is the number of hypermultiplets minus the number of vector multiplets is 273 minus 29 times the number of tensor multiplets. This is probably the most famous anomaly cancellation formula in 6 dimensions. And this is the thing which really is controlling the scope of possible theories you can get. Basically, this is like the partition bound. You know, in looking at intersecting brain models or any other kind of thing, you have this tadpole constraint, which you can not oversaturate because there's some causative contributions. This is roughly like that. We can think of this as H equals, for a given number of tensor fields, this is H equals 273 minus the number of tensor fields plus the number of vector fields. That means for a given number of tensor multiplets and gauge group, there's only a finite amount of matter you're allowed to add into the theory. So there's a restriction to how much stuff you can put in before you violate this. This is going to be really the thing which bounds us in our attempts to bound the set of theories. Now let me parse the F to the fourth equation. There's some funny things appearing here. XIR is the number of matter fields appearing in representation R of the gauge group GI. So this guy here is the number of fields in representation R of the gauge group GI, and we're summing over all representations. So this is a sum over all the matter fields which are contributing to the anomaly. And there's coefficients here, B's and A's and C's, and these come from expanding the trace of F squared and the trace of F to the fourth in terms of the trace in the fundamental representations. And these are just group theory identities. Basically, trace in an arbitrary representation of F squared is just a number, a positive number, in fact, times the trace in the fundamental. And these are easy to calculate for any given representation for, say, SUN. You can just write down an explicit set of generators, you know, delta ij, delta KL, whatever, and calculate in a given representation what this coefficient is. Trace F to the fourth in a given representation can always be expressed as a linear combination of the trace in the fundamental of f to the fourth and the trace of f squared squared in the fundamental. So those are just some constants. And for later convenience, I put some of these constants up here. So this is just, in the fundamental representation, obviously the trace of f squared is equal to the trace of f squared. So we get a 1. B is 1. And since trace of f to the fourth is trace of f to the fourth, there's no c, so that's 0. And you can do a little exercise for, say, the adjoint of SUN or the antisymmetric or symmetric, and you can calculate those numbers. I also put the lambda values for SUN, which is 1, and SON, which is 2, there just for convenience, because we'll use them. So we know what all the pieces are now, and the other pieces, the other 4 equations here, are the cancellation conditions, which basically, if you look at this product, this thing breaks, you just use the distributive law. There's 3 different terms here. Well, there's 4 different kinds of terms. There's terms from A dot A, which come from trace r squared times trace r squared. So the anomaly proportional to trace r squared times trace r squared is going to constrain the inner product of the A vector with the A vector. And when you work it out, that turns into A dot A equals 9 minus the number of tensor multiplets. It's a lot like in 10 dimensions where we had this n minus 496. Right? We had to have a rank of the gauge group as 496 in 10 dimensions. A dot A has to be 9 minus t. Maybe the n minus 496 might be a little bit more like the r to the fourth. Sorry, I lied. This is like the n minus 496. There's this r squared condition which says that A dot A is equal to 9 minus t. There are cross terms between the a's and the b's, which tell us about the trace r squared, trace f squared. Those end up being given by a trace by the adjoint A minus a sum over all the matter in an R representation of the A's, and the bi dot bi is similarly given by some sum over the C's. And finally, there are cross terms between the B of one vector, one gauge group component, and the B of another gauge group component, bi dot bj, and these are important because these are given by a sum over all the matter which transforms under both gauge groups. So xijrs means something which transforms under gauge group I in representation R and gauge group J in representation S for I not equal to J. These are the charged fields which transform under more than one gauge group. And the important thing to note here is that the A's are positive, and therefore any time the inner product of two B's is positive, there is always matter charged between those two gauge group components. And that's going to be a very important piece of what we need to constrain the number of possible theories. So I kind of told you what the pieces are. I'm going to do an example, but let me just stop for a moment and see if anybody has any questions about any of those pieces. Yes?
So xij's, so they represent hypermultiplets which transform in the bifundamental?
They could be bifundamentals. They could be a fundamental times an adjoint. They could be something in the threefold antisymmetric representation times something in the... They could be something which transforms under 5 different gauge groups. In fact, there are theories which have matter fields which transform under 3 different gauge groups. You don't see them in the sort of more straightforward string constructions like intersecting brane models because there's no strings that stretch between 2 things, but you can have string junctions which stretch between 3. And in F theory, you can see this. And I'll describe when we get to F theory how you get these kinds of exotic representations. So this seems a bit complicated, but the reason it's a little abstract is because this is very general and it includes all these kinds of exotic things like trifundamentals and things in funny representations. So it's a very general framework which would hold for any 6-dimensional gravity theory and will allow us to constrain what you can get.
So,
Yeah.
It's a related question. So when you take the sum of representations in the line like XIR, CIR,
Mm-hmm.
so there it's sum of, so suppose X is a trifundamental. So how
Yes.
does sum work out there?
You count the okay, it's good. So let's say you have an SUN cross SUM. Lost all my things. Basically, you count the number of things which transform as the fundamental of the first thing. So if, for instance, we have an SUN cross SUM with a bifundamental, say like that, that would go to X sub fundamental, X sub 1 sub fundamental equals M. Right? There are M different pieces in this fundamental, each of which transforms as a fundamental there. If it was a trifundamental, you'd multiply M1 by M2, et cetera. So let me do an example, which hopefully will make this all a little clearer and will be useful. Actually, I'm going to do the example over there so I can leave it up for a little bit. So, oops. So let's say we have a simple kind of gauge group, which is just SUN. Okay, and let's say we have F fundamentals, A antisymmetrics, and D adjoints. Okay? So let's say I want to build a six-dimensional supergravity theory in which there's a gauge group SUN, and it's got F fundamentals, A antisymmetrics, and D adjoints. Let's read off what some of the anomaly cancellation conditions say. So the key one I want to focus on is, for starters, F to the fourth. The F to the fourth condition says that the B for the adjoint, so where's the B for the adjoint? B for the adjoint is 2n, minus the sum over all representations of the number of things in that representation times the B for that representation has to vanish. So the number of fundamentals is F minus F times the B for that. So the B for the fundamental is 1, so minus F, minus, then we have A antisymmetrics. That has to multiply by n minus 8. And then we have to subtract D times the number of adjoints, which we already did, minus D times 2n equals 0. Okay? So that's the F to the fourth anomaly cancellation condition for this set of theories. Unless the number of fundamentals is related to the number of antisymmetrics and adjoints through this formula, anomalies will not cancel. So let's look at a couple special cases. Let's say D equals 0 and A equals 0. Or let's just say D equals 0. If D equals 0, now let's say D equals 0, A equals 0. D equals 0 and A equals 0, those guys cancel. Then F equals 2n. So if we have a theory with only fundamentals and a gauge group SUN, it's got to have 2n fundamental matter fields. If D equals 1, let's say, then this term cancels this term. Then F equals A times n minus 8. Okay. In particular, if n equals 8, we get F equals 0. So if we have one adjoint, we don't need any other matter, which is pretty clear because if we have one adjoint, then B adjoint minus B adjoint is 0, and the equation is satisfied.
I think it should be 8 minus.
What's that?
They both have minus.
So if D equals 1, which thing are you objecting to?
So F equals
A times n minus 8.
8 minus, I guess, because they both have minus.
Oh, good, good, good. Yes, you're absolutely right. This is 8 minus n. Thank you. Doesn't matter for the n equals 8 case, but it matters for the other. Good, excellent. Good. Okay, so that's what the F to the fourth, yeah.
But in that case, what if n larger than 8?
Then there's an anomaly which you can't cancel. And your theory is dead in the water. Other questions? Move this thing, which I keep bumping into. Okay, let me just follow this example one step further and write down the A dot B and B dot B anomaly cancellation conditions, because we're actually going to use this example a little later, so it's useful to have it all on hand. So I mentioned, let's specialize to t equals 1. So if we specialize to t equals 1, as I mentioned, we can write A as minus 2 because we know A squared equals 8, and we can, by linear transformation, leave this matrix unchanged and put A in that form. So the only thing we don't know is B, which we're writing as 1/2 alpha alpha tilde. So I can now write down the equation minus A dot B, which is equal to alpha plus alpha tilde, just dotting those guys together. And that's equal, this A dot B equation. I've changed the sign because this A is generally something negative, so we want to change the sign. We get 1/6. Lambda is 1 for SUN, so it's the right normalization. And then we get A of the adjoint. A of the adjoint for SUN is 2n. Sorry. Since I changed the sign, it'll be minus 2n. And then it'll be plus. And let's look at this case right here, where we have 2n fundamentals, or we have some number of fundamentals. 2n plus f equals 0. So in this case, where all we have is fundamentals, and there's 2n of them, minus a dot b vanishes. So alpha plus alpha tilde is 0. And then the equation for b dot b is that b dot b, which then is equal to alpha alpha tilde over 2, because it's alpha over 2, alpha tilde over 2, dotted into itself, so you get a factor of 2. It's alpha alpha tilde over 2. We can read it off from that second to last equation. It's 1/3 times, and then we have the number of fundamentals times the c for the fundamentals, which vanishes, minus 6. For the adjoint, this is minus 2. So alpha plus alpha tilde vanishes. Alpha alpha tilde over 2 is minus 2. So b dot b is minus 2. So the upshot is, for these theories here, erase this little line here. For those theories there, we have b is equal to plus minus 1 minus plus 1, and alpha comma alpha tilde is equal to plus minus 2 minus plus 2. One of those two choices. These don't determine which is alpha and which one is alpha tilde. Okay, so that's just an example of solving the anomaly equations. We've found some low energy theory which seems to satisfy the anomaly conditions. It's a theory with a gauge group SUN, 2n fundamentals, and we can read off what the a dot b and b dot b conditions are, which determine alpha and alpha tilde in the t equals 1 case. Okay? Any questions about that? The idea is, first of all, we're going to use these constraints to show that there's only a limited set of theories you can actually have. And then what we'll see is that this data that you get from the anomaly can be very helpful in trying to understand the structure of the theory. In particular, what we'll get to at the end of the day is that when we do F-theory compactifications, the data we get out of F-theory matches perfectly with the data that we're getting out of the anomaly cancellation conditions. So there's a dictionary between F-theory and low-energy theories is made very transparent by the form of these anomaly equations. So any questions on that? Okay, so I just wanted to go through one example so we can kind of get a little feel for what's going on here. Now there's a remarkable fact, which is that with these normalizations I've stuck in here, these lambdas, all of these inner products, a dot a dot b, etc., are all integral. In certain cases, that depends upon the absence of global anomalies. For instance, there are some gauge groups which don't have a invariant fourth order Casimir, so you don't have this b. And for those, you need to include cancellation of global anomalies. So I'm not going to go into the details of this, but the fact is that these guys are all integers, and therefore the anomaly conditions determine for us a lattice. A lattice with basis vectors, which are the a's and the b's. It's a lattice of signature 1 comma t. And as we've seen in all these higher dimensional compactifications, lattices play a big role. So that'll be helpful to us. Questions?
Wait, so this lattice is coming up in a pretty different context than before.
Would certainly seem so. Would certainly seem so.
Okay.
But as we'll see, it's related to lattices that appear in the string compactifications through more familiar mechanisms. Okay. Other questions? Okay. So I'm going to go over briefly for you a proof of the fact that as long as t is less than 9, when you have fewer than 9 tensor multiplets, there are a finite number of possible gauge groups and matter representations which you can get. So for t equals 1, this is in a paper that Vijay Kumar and I wrote, and for t up to 8, it's in some work with Dave Morrison, which should be appearing soon. I'm just going to give the schematic of this proof here. I want to go through it because understanding how to bound the number of theories gives us a very good feeling for what the set of possible theories is, and where there are regions of theories that we may not be able to realize in string theory because the set of theories might run off to infinity, in particular for large t. I want to understand what kinds of theories those are that have this odd behavior of having infinite numbers of realizations. Okay? So I've got two transparencies where I'm going to try to go through two pieces of this proof, and then we'll go on to constructing some specific string vacua. Are there any questions about this or what I'm going to try to prove? The key thing that I'm going to use here is really there's two pieces. There's this piece right here, which is, as I said, kind of a tadpole condition. That's something we can't oversaturate. And then, as I mentioned, there's this piece right here, which says that any two gauge group components which have an inner product bi.bj, which is positive, have to have matter transforming under both gauge groups. So let's try to prove this. We're going to prove that there's a finite number of possible models with t less than 9, or finite possible combinatorial data, at least. How do we do that? Well, if we fix the number of tensor multiplets and we fix the gauge group, then, as I argued before, there's only a finite number of possible matter representations you could have because there's this bound on H. You can only have up to a certain number of matter fields. They can only live in a finite number of different representations if you have a fixed group. So the only way you can have an infinite set of theories is if G can become unbounded. So if there's some infinite family of theories where G becomes unbounded. And there's two ways that could happen. One way it could happen is you could have a gauge group like SUN, and the n could go to infinity. And the other way it could happen is you could have a product of gauge groups where the number of factors goes arbitrarily large. So first, let's address the case where the number of factors gets arbitrarily large. So if we assume that there's k factors in the gauge group, and that each one has a maximum dimension of d, then we can use this geometry of the 1, t space to put a bound on the number of matter fields. And basically, it comes from this bifundamental story, or not necessarily bifundamentals, but things transforming under multiple things. Basically, the B vector for any given gauge group either has a norm squared, which is positive, 0, or negative. That's definitely true. So let's say it's positive. If B squared is positive for a gauge group factor, then we can write it as x comma y vector in 1, t space, where x absolute value is bigger than the norm of y, right? Because norm squared is x norm squared minus y norm squared. If that's positive, this thing happens. But if that's true for two vectors, b and j, bi and bj, then their inner product has to be positive. So any two vectors, bi and bj, which both have positive norm squared, will have to associate with gauge group factors between which there is some matter charged. So there's there's some matter which is charged under both of those gauge groups. So if all of our gauge group factors had positive b's squareds, then there would be matter charged under every pair, and we would have order k squared matter multiplets. And you can be a little more careful about that argument, but basically this implies that we can have at most square root k of these positive type things. It's a little more elaborate for the negative norm ones, but basically, if two negative norm states are to have no matter charged under the two of them, they have to be orthogonal. And we can't have more than t or mutually orthogonal negative norm states, negative norm vectors, right? Because that would be a basis for a greater than t dimensional space, which we can't fit in R1t. So at most t of these things can be mutually orthogonal. So let's say we've got n b's. We can make a little graph, and we can connect every pair which are mutually orthogonal. There's a bound on how many edges we can connect without having t plus 1 of them all connected to each other. And that bound is of order 1 over t on the total number of edges, which means that we have to have, if there's n nodes, we have to have n squared edges unfilled, really n squared over t. And that means that, again, we have matter charged, that we have order n squared matter fields. And so once again, we have at most square root of n, k type these guys. And basically, without getting into too much of the details, this shows that the only way you can have a very large number of these factors is if they all are negative norm and parallel. And then if you just do some case-by-case checking, you find that every gauge group with matter, which has a negative norm, which has a 0 norm b squared, has a positive value of h minus v. You just check in a finite set of cases. And that's this tadpole constraint, and you can't have almost all of your things having a positive contribution because then you would exceed the tadpole. So for any value of t, you can't have this product of an infinite number of factors. We've totally ruled that out. You'll never get an infinite family that way. The other option is a little more relevant to what we're going to see later. That's where one of the gauge group's factors becomes infinite. Yes?
So does this somewhere put a bound on k, or is it just showing that k cannot be infinite?
Yeah, this in principle does put a bound on k. And in fact, you can use, I'm not going into it, but you can use this, the method of this proof to actually generate algorithms for essentially scanning the set of all possible solutions of these equations.
I mean, given a gauge group, or can I put a general one?
You can scan over the gauge groups too. I mean, for instance, we've actually done a complete scan over all gauge groups which are products of SUN with certain limits on the set of representations. It's a little tricky, but you can use this kind of bound to turn into an algorithm where you can actually figure out how big the thing can be. Yeah, so the answer to your question is yes. I don't want to go too far down that road. So I threw in this additional constraint at the beginning. And the key there is that without this additional constraint on the gauge kinetic terms, there are infinite families of theories which satisfy just the anomaly cancellation. John Schwartz found one of these infinite families quite a few years back. He pointed out that if you take SUN cross SUN gauge group with two bifundamental matter fields, then you satisfy all the anomaly cancellation conditions. And we actually just checked that, right? We just checked that if you have an SUN gauge group with two n fundamentals, then you satisfy the anomaly equations and everything's okay, right? So he pointed this out, because here you have 2n fundamentals, because there's 2n here, 2n here. And it turns out there's several other families like this. There are families with various product groups, and when you go up to t greater than 1, there are 3 products. But there's only a finite number, and you can classify them. So it looks like there are these infinite families of models which satisfy anomaly cancellation. But they have a common problem as long as t is less than 9. When t is less than 9, then a squared is greater than 0. Right? And remember, we wrote down these equations here. A dot b vanishes, so a is orthogonal to b, and b dot b has -2, right? And that meant that there were 2 possibilities for b. It's either +1 -1 or -1 +1, right? So that means for each of the 2 factors here, b1 and b2 each have to be taken from this choice of +1 -1 or -1 +1. But if you compute b1.b2, which has to be positive, that's the number of bifundamentals here, because the a's are 1, we get 2. So b1 and b2 can't be the same, because then b1.b2 would be -2. So therefore, b1 has to be one of these options, and b2 has to be the other one with the opposite sign. Right? So therefore, b1 is equal to -b2. That says b1 plus b2 equals 0. But that means that j dot b can't have the same sign for both of those 2 things. So that infinite family must be sick because one of the gauge kinetic terms is going to vanish. You can say this more generally. This basically rules out all these infinite families here. For all of them, a dot, the sum of b1 plus b2 vanishes, while b1 plus b2 squared vanishes. And as long as a is positive norm, that means this thing here means that b1 plus b2 squared is negative unless b1 plus b2 vanishes. So we can derive the fact that b1 plus b2 vanishes up to t equals 9, and then we can't. Okay? Okay, so that's the proof. Up to t equals 9, there's a finite number of possible models. At t equals 9, suddenly we lose control by this method. Any questions?
So I see for this particular case that Schwartz came up with, it fails at t equals 9. I mean, are there perturbations thereof that you could...
We've systematically analyzed all the possible infinite families with a large gauge group. It's actually not hard to do because if you have a gauge group factor SUN or something, which is getting big, there's not too many different representations you could have without exceeding the tadpole bound because most of the representations grow faster than n squared. So it's really just the fundamental, the adjoint, the antisymmetric and symmetric. And you can just look at you can list the possible combinations and show that these combinations I've got here, basically there's 8 combinations. Those are all the combinations, and you can use this mechanism to rule it out for all of those combinations up to t equals 9.
So did his case hit to you guys that 9 is special, or did you sort of went from there?
No, actually, we first spent a lot of time thinking about t equals 1 and found this argument for t equals 1. And then it was only later that we started to try to analyze more tensor fields and discovered that, strangely enough, the argument works perfectly well up to t equals 9. And then at this point where a squared becomes negative, which will have a geometric significance that we will talk about when we get to F theory, we lose control. Questions?
So your proof for case 1 is valid for any t?
The proof for case 1 is valid for any t. That's correct. It is not true for unbounded t. It is true for finite fixed t. Strangely enough, we can find an infinite family of theories with E8 to the k where t grows with k, which is okay by the point of view of anomaly cancellation and the Sanyoti constraint. But those don't seem to appear in string theory. Okay, questions? Yes?
Is there any intuitive way of seeing why the number of tensor multiplets displays such an important role? I mean, with reference to your
Well, it has to do with this equation, h minus v equals 273 minus nt. At this value of t equals 9, that becomes negative, and you're sort of dominated by vector things. The most important thing, actually, is this fact that a squared equals 9 minus t. Because when a squared becomes negative, a ceases to be a positive definite vector, and it's really the positive definite nature of a that is playing an important role in constraining what's going on. So basically, I mean, my feeling is that there's going to be some other constraint which we don't understand yet, which will help out when a squared is negative. But there has to be some additional constraint that will come in order to bound this set further.
But could you just remind me where the 9 came from? Like the 9 in a
That came from the anomaly cancellation condition. If you do the explicit calculation of the gravitational anomaly, it comes from the gravitational anomaly cancellation of the form r squared, r squared. And we'll actually see more geometric meaning to this 9 when we get into when we get to the F theory compactifications in particular. It's got a lot of geometrics. It's related to the, if you know anything about Del Pizzos, there's a Del Pizzo thing. Which, funny things happen at 9. Okay. Yes, Oliver.
Just maybe you want to defer this until you talk about Del Pizzos. Is there any E sub n exceptional symmetry structure associated with the E sub t, I should say, with the number of tensors?
Not that I know of. It's a really good question. We can get E8 all the way down to t equals 1. I mean, you can get theories with an E8 gauge group at t equals 1. You know, we can get those from the heterotic in particular. So I don't know of anything special that happens with those E groups as you go up.
There are also theories of global symmetry that are exceptional.
It may be that there are global it may be that there are global symmetries, and there's certain things which become infinite at t equals 9. Not only the number of things, but you know, there's a lot of stuff which is relevant at t equals 9. Let me talk about that this afternoon a little bit. Okay, so you might ask, well, maybe we're just not smart enough to think of a way of ruling out theories at t greater than 9, but maybe they're still bounded. And that's not true. We can actually write down a Schwartzish, a theory like those that Schwartz wrote down at t equals 9. He wrote down his theory at t equals 1. But we can write it down at t equals 9, this SUN cross SUN family. We need to solve these equations. Minus a dot b equals 0, and b dot b equals minus 2. And if we go into a basis where the omega takes the form plus and then all minuses, and we take j, which is just 1 and then all zeros, then here's an example. We take a to be 2, 1, 1, 1, 1. That's 4 minus 4 is 0. So a squared is 0. A dot b is 2 times 1 minus 2 is 0. You can check it for yourself. It all works out. So there are infinite families of apparently consistent low-energy theories. Yes? There are these infinite families of apparently consistent low-energy theories that we don't know how to roll out from low energy, which are compatible with anomaly cancellation and this sign constraint.
So in order to these theories, they have global symmetries.
It is possible that you can use global symmetries. It's not something we've really explored. It's a good question. Some of them will have global symmetries. There's a structure to the moduli space that we know a little bit about, but not a lot about. It's kind of an open ballgame. I mean, I can tell you that these theories exist, and there's all kinds of things I could imagine exploring about them, and we've only touched the surface of that.
You could use that as a constraint to eliminate theories by saying all the ones that have continuous global symmetries throughout.
Mm.
I don't know how powerful.
You wouldn't know with the quantum mechanics breaks them down to discretes.
Right.
Supergravity
Yeah, I mean, in fact, there is, I think, an interesting story related to that, which is these do all have global symmetries, and they probably are all broken in the quantum theory, and that actually has to do with this lattice that I've been talking about. Not going to deeper into that. Okay, so let me summarize where we are so far. If we analyze the bounds on possible theories in 6 dimensions, which are supersymmetric theories of gravity with one supersymmetry, each theory has associated with an integral lattice. So, for instance, for this theory here, the integral lattice is, for t equals 1, we would have an integral lattice of the form, that's 8, good, 8, 0, 0, minus 2, where this is a squared minus a dot b minus a dot b, b squared. So that's a lattice, 1, 1 lattice. We have a finite number of possible gauge group and matter combinations for t less than 9, which in principle we can enumerate, and there are infinite families at t greater than 9. So that's kind of the big picture of what we can get. And now what I want to do for the rest of the discussion of 6 dimensions is to talk about what we can get out of string theory. Okay. So any questions on the this is the big red circle, G, except it kind of goes off to infinity. So there's our G. And now we want to fit in string vacua. Any questions about G? Yes?
I'm not sure you said this explicitly, but is the field strength for each b mu nu contains the corresponding A and B factors?
Yes. In fact, they appear in the Lagrangian. It's just like the usual Chern-Simons terms in B. It's H equals d b minus A omega, that kind of thing. Okay. So I'm now going to go through these various different approaches to 6-dimensional string compactification. I think that 6 dimensions is a really excellent playground in which to try to understand compactification methods. They're already very rich and have a lot of structure because we've got matter and representations, but they're simpler than 4 dimensions, and we can kind of get a more complete analytic handle on them. And most importantly, these anomaly cancellation conditions provide us with extremely strong checks on what we're doing. So if you think you have a consistent vacuum construction, you can try to put it together and then check the anomalies. And through historically, people have used this very much in the F-theory constructions and various other constructions to try to understand the validity of a new kind of vacuum construction. So the 3 things I'll talk about are intersecting brane models, more about heterotic, and F-theory. And in this lecture, in the last 20 minutes or so, I'm going to tell you a little bit about intersecting brane models in 6 dimensions. So you've heard in Miriam's lectures lots of things about intersecting brane models. So I'm just going to kind of review some of the points which I think she's touched on and give you kind of the basic picture of what we're doing in 6 dimensions. And then we'll see a little bit about how those fit into this big picture. Okay, so the idea of intersecting brane models, as you know, is you compactify on some space, and then you wrap some branes. And the branes give you gauge groups, and the intersections between the branes give you matter. And that's all nice. It gives you nice things which look a little bit like real physics. More and more like real physics as you get down to 4 dimensions and tune things more carefully. The first problem you run into, of course, is that you can't just have d-branes. D-branes carry Ramon-Ramon charge. And if you have a compact space, you can't just put a bunch of charged stuff on it without canceling the charge. If you try to have d-branes and anti-d-branes, you'll break supersymmetry. So to have supersymmetry and d-branes, you need to add supersymmetric orientifolds. So let me just quickly review orientifolds. And this will bring us back to the type 1 string and its connection with type 2b. So again, I think Miriam's talked a bit about orientifolds, but let me just kind of go over the main points, maybe in a slightly different way. So the string reflection, the omega action, reflects the string, takes the right movers to the left movers, the alpha oscillators to the alpha tildes, and simplifies the spectrum by removing some of the states. For instance, the B field, which gives you a -1 under string reflection, because if you flip the alphas and alpha tildes, this picks up a -1, goes away. So in type 1, you have D strings, and you have a quote-unquote Ramon-Ramon B field, but you don't have a regular NS-NS B field. And Joe did this nice calculation for us where you can do a tadpole calculation and determine that the orientifold carries Ramon-Ramon charge. It has negative tension and it has negative d-brane charge. In 9 dimensions, it has 16 units of negative d brane charge. And because of this, these orientifolds become a key player in all kinds of vacuum constructions, because when you put an orientifold in, then you can add d branes, and you still maintain supersymmetry. You don't have charges which aren't canceled, etc. And as we'll see in a minute, we can combine orientifold, the string reflection omega, with reflection in space-time to get lower dimension orientifold planes. But basically, type 1 string theory is what you get when you take type 2b, you mod out by omega, and therefore you get string theory with an O9 plane in it. 16. This O9 plane has a charge which needs to be canceled by d branes, so we can think of that as 16 d branes and their images, and that gives us an SO32 gauge group. Basically, if we take the d branes, I keep leaving my chalk over here. If we take the d branes, there are a bunch of U1s associated with the different d branes. In an SO32, these become like the 0, 1, minus 1 zeros associated with the 16 d branes. And then the orientifold reflection takes the degrees of freedom between the strings, between the branes and their images, and mods out half of our degrees of freedom, so that AA and A prime are mapped to each other, AA prime to A prime A, etc. So instead of 4 complex degrees of freedom, we have 4 real degrees of freedom going between each pair of branes, or branes and their images. That gives you, after the quotient, an SO32 gauge group. So that's the identification between type 1 string theory and this quotient of type 2. And by systematically doing T-duality, we can describe O-planes in all kinds of dimensions. We remember our discussion of T-duality. The mass spectrum is invariant under switching R to alpha prime over R and winding and momentum. And that acts in various ways on the various pieces of the theory. It takes the right movers, gives them a minus sign. It takes a dp brane and turns it into a dp plus 1 or a dp minus 1 brane, because it changes Neumann boundary conditions to Ramon boundary conditions. I think Miriam put that on the board the other day. If you change the dimension of the d brane, if you start with a 9 brane, it's got a gauge field on it. If you T-dualize in a direction mu, the gauge field component A mu now becomes a perpendicular direction, and that becomes a spatial function x mu, describing the position of the T-dual brane. So a brane, a 9 brane, T-dualized on a circle will go down to an 8 brane, which is just localized at a point. An orientifold plane will also go down a dimension, because we get, combined now with the orientifold action omega, we get a sigma, which reflects the circle. But that orientifold reflection sigma in space-time on a circle has 2 points. So the orientifold, unlike the d brane, splits up into 2 orientifold planes after compactifying on a circle. And since the total charge has to be the same, the charge of each of those O-planes goes up or down by a factor of 2. Here the charge goes down by a factor of 2. So if we start with an O9 and 16 D9 branes, each time we T-dualize, we get a factor of 2 more O-planes with the same number of D branes. Okay, so that gives us a picture of what the charges are on the O-plane, which we need to cancel with D branes. So to build an intersecting brane model, we want to take some space and put branes in it which intersect. So Miriam went through a detailed conformal field theory calculation, I think yesterday perhaps, of the condition for intersecting branes to preserve supersymmetry. And for branes that intersect in 2 planes, that is in 4 spaces, in 4 dimensions where we have a 1-2 plane and a 3-4 plane, so there are 2 intersection angles. The condition is much simpler. The condition is just that the 2 intersection angles are the same with an opposite sign. I should really, to make this more clear and precise, I should actually have included orientations here. So this should really be oriented that way, and this should be oriented that way, this way, and this way. We'll need that more in just a second. So we preserve supersymmetry when the angles are opposite. There's a T-dual picture in which this is essentially just the self-dual or anti-self-dual condition on an instanton. So if we put in branes, we can preserve supersymmetry with this angle condition. The same is true for D branes intersecting O-planes or O-planes intersecting O-planes. So let's look at the simplest kind of thing we can get in intersecting brane models, which is a 6-dimensional intersecting brane model, which we'll do by taking the K3 and presenting its limit as an orbifold, which we talked about yesterday, and taking an orientifold of that. So you could say, why not just do a torus? But if you just do a torus, you can't put anything interesting in. All you have is an O-plane, which is parallel to one of the directions of the torus. The D-branes all have to be parallel to that same direction, and it's just equivalent to the compactification of type 1. So the first interesting thing we can get, it's got more supersymmetry as well. The first interesting thing we can get is this K3 compactification. You could try to do it on a continuous K3, but it's a bit harder, and people have not really explored that as much as these orbifold limits. So I'll just do the simple orbifold limit, and we'll see how that works here. So we're going to take our K3, which as we described yesterday is a T2 cross T2 with an orbifold action which inverts both z's. So z1 and z2 both go to minus z1 and z2. And again, I should give this an orientation. So this one goes like this, and this one goes like that. The orientifold action is going to take zi to zi bar, so it reflects across the horizontal axis in both planes and gives us an orientifold 1,3 plane. That's an 0,7 plane. It's stretched in those two directions. Right? Now, if we're going to orbifold by a z2 action, this rho, and we're also doing a quotient by this z2, omega sigma, we also have to quotient by omega sigma rho. Oh, shoot, my arrows all disappear every time I do this. Okay. This guy's oriented like this. This guy's oriented like this. And the important point is that this guy's oriented down. The combined orientifold action, if you just look at the action of sigma times rho, if you take z, go to minus z, and then reflect it, you're now reflecting across the vertical axis. So on the orbifold limit of K3, we have to have not only an orientifold plane on the horizontal, but also on the vertical, which we're going to have to cancel. This is the second 0,7 plane. Okay. So here's a simple intersecting brane model. We take that orientifold of the torus, and now we want to wrap D7 branes on cycles of those two tori in such a way that we cancel all the orientifold charge. So the winding of a D brane can be characterized by some winding numbers nm. N is the winding number here, n1, m1. So this is a 1, 1 winding. This is a 1, minus 1 winding. Again, I'll have to put in some orientation here, like that. The lighter blue is the orbifold image. And of course, as soon as I go to the next layer, those arrows will disappear. So fix those arrows in your mind. So we describe this as a 1, 1, 1 minus 1 thing because we've T-dualized twice. So this guy is going to have, so we want to have a total of, I always get the factors of 2 mixed up. Let me make sure I'm getting it right. So we've done the orbifold, and as well we're doing the orientifold. So the orbifold carries twice the value of the unorbifolded orientifold. So we've gone down by 2 dimensions. So we get 16 down to 4, but then we double it because of the z2. So we get 8. So we should be able to cancel this with 8 branes that are wrapped diagonally in this direction. Right? The wrapping in the 1, 3 direction should cancel the tadpole in the 1, 3 direction, and the wrapping in the 2, 4 should cancel the wrapping in the 2, 4. So officially, the constraints that we need to impose are the SUSY condition, which says that the angles have to be equal. And that, on these winding numbers, says that m1 over n1 is minus m2 over n2 multiplied by some proportionality constant because we're allowed to stretch the tori relative to each other. And then there are tadpole conditions, which say that the total charge of the D branes, if we have n branes wrapped on cycle A, which is characterized by these winding numbers, the total charge in the 1, 2 plane has to be 8, in the 1, 3 plane has to be 8, and the total charge in the 2, 4 has to be minus 8. So those are the tadpole conditions. And we can see that these are all satisfied by this thing here. So let's look at what the physical content of this example is, and then check to see that it satisfies anomaly cancellation. This is a check to make sure that what we're doing is correct. The gauge group is SU8 because it's 8 wrapped branes. There's one tensor multiplet because this is a reduction of a supergravity theory, so the only tensor multiplet comes from the B field in 10 dimensions contracted down to 6 dimensions. There's one matter representation in the adjoint coming from the fact that this is a D brane moving around in space. You always get one matter representation in the adjoint, basically coming from the 10-dimensional vector. There are no fundamentals because this one doesn't actually intersect anything. There are 4 antisymmetrics coming from the fact that it intersects its image. It doesn't intersect any other branes because we've only got one brane stack. There are 4 antisymmetrics which you can compute by taking the intersection between the brane and its image and the brane and the orientifold and taking the orientifold action. I'm not going to go through that calculation, and perhaps Miriam will touch on some of that. But that's the matter content. And now we can check, does that satisfy our anomaly cancellation condition? And we had this equation we wrote down over here. And we have a case where D equals 1. And when D equals 1, that led us to F equals A times 8 minus N. And N is 8. And so F is 0. So everything works. OK. So that's an example model in 6 dimensions. We get it by doing this intersecting brane construction. And we can check it satisfies anomaly cancellation. So just for fun, let me give you a little homework exercise, which will be a little exercise both in the intersecting brane model construction and also in checking the anomaly conditions, the thing we did at the beginning with these A's, B's, and C's. Let's say you have a model which looks like this. Should have done that in black, I guess, because the orientifold plane is here. It's the same thing I've got over there, orientifold like that. And then we have, let's say, a brane which wraps 1, 2 and 1, minus 1. And then let's say we have a brane that wraps like this on the orientifold plane, which is going to be 1, 0, 1, 0. And the homework is compute the spectrum and check anomalies. And just to help you out, here's sort of the systematics of orientifold of intersecting brane models on a K3 orbifold. I think Miriam's going through a lot of this, but there's a paper I'll just reference which has some of the explicit calculations that you need to do to get the representations and the factors of 2 right, which are a little tricky because of all the orbifolds and things. Basically, we're always wrapping these branes on the bulk cycles. The ones, remember we broke up the H2 of K3 yesterday into the U plus U plus U part, and then there's the parts that are localized at the singular points. And all these cycles are wrapped on the U plus U plus U. Because of the orbifold, the intersection form carries an extra factor of 2. Because there's because of the orbifold, so there's an extra intersection for every intersection you see. The total charge, brane charge associated with the brane is just gotten by taking the different winding numbers. The orientifold, as I mentioned, has a charge which is an extra factor of 2, again because of the orbifold. And you can compute the matter representations. Most of these you can see quite readily. How many adjoints do you have? Well, you have one adjoint because a brane always has adjoints. And then every time you have a brane moving in an external space, every time the brane crosses itself, you get an intersecting brane string stretching between the brane and itself. That's an adjoint. If those are two, if this is A and this is A, then that's an adjoint. And if it's A and B, say, then it's going to give you a bifundamental. If it's B prime, the orientifold image, then the orientifold image, then you're going to get these guys. And then when you symmetrize and anti-symmetrize, the orbifold action, which I won't go through, gives you these formulae. So anyway, I'm not going through more details. I know you're learning a lot about this in Miriam's lectures, but just to give you a flavor of the kinds of things you get in intersecting brane models, one thing I want to point out is that the combinatorial range of models here is fairly bounded, particularly because of these tadpole cancellation conditions. right? Here are the tadpole cancellation conditions. These guys here, the sum of these has to equal 8, the sum of these has to equal 8. These numbers are always positive, and there's not too many combinations of products of numbers which add up to 8. So you can actually kind of by hand just write down a pretty wide range of the possible models you could get in this construction. You can get more sophisticated by including the fractional cycles on the K3, right? We've talked about the fact that the K3 cohomology or homology actually has these extra cycles coming from the singular points, and then there are fractional branes, which are half of the bulk cycles plus fractions of the exceptional cycles. And so there's some nice analysis of that by Blumenhagen and company, which ends up being closely related to Jumon-Polchinski constructions of six-dimensional models in a more type 1 context. Again, you might want to do this away from an orbifold point, but it gets a little bit harder. Yes, please.
Is it just one brane on each?
Oh, I didn't give you the key piece of information. There's 4 of these and 4 of these. And you should check that that satisfies the tadpole conditions. Thank you. It wouldn't satisfy the tadpoles without that. You need 4 of each of them. I've given you everything you need to figure out the spectrum on this brane. This one you might find a little subtle. Note that this is wrapped on the orientifold plane, and therefore it may actually be an SO group rather than an SU group. And so you might have to think a little bit more about how to get that to work out. That was what I wanted to say about the intersecting brane models. Let me close maybe with an anecdote about intersecting brane models in 4 dimensions, unless there are any questions right now. Okay, so let me spend, if I may, started 3 minutes late, so I'm going to take 3 extra minutes. Let me spend, if I may, 5 minutes telling you about how this story becomes richer in 4 dimensions. So in 6 dimensions, as we've just seen, there's not a wide range of models you can construct. In 4 dimensions, on the other hand, there have been many, many papers where people use an analogous construction to get intersecting brane models with semi-realistic phenomenology. Miriam, I'm sure, will tell you about some of them. Much of this work is based on a very similar thing to what I just described here, a T6 mod Z2 cross Z2 orientifold. So there's a lot of beautiful work on this, focusing on trying to find phenomenologically realistic models. I want to tell you about a little bit of work in which the question was not, can we find something realistic, but what kinds of models can you get in this construction? In particular, how big is this set? I'm kind of focusing here on global questions. Are there a finite number or an infinite number of vacua in some given construction? Are there a finite number or an infinite number of supergravity theories allowed in some context? So you can ask, here's T6 mod Z2 cross Z2. It's basically just like the case we just talked about, except now you have 3 tori. And the Z2s are -1, -1, and -1, -1. And of course, if you take the product, you get -1 here and -1 here. So you have now 4 orientifold planes. You've got an orientifold plane here, and then here, vertical, vertical. And there are tadpoles, which just like we had there's a tadpole P, which is N1, N2, N3, Q, which is minus N1, M2, M3, R, which is minus M, N, M, and S, which is minus N, M, M, N. And the tadpole constraints are that the sum of the P's equals the sum of the Q's equals 8. So it's not me, is it? No. Okay. So you can ask, are there a finite number of solutions in this case? And I just argued it's really simple in this case to show that there's a very bounded set of solutions. It's much more subtle in this case because your typical brane with various winding numbers, typical branes are going to have P, Q, R, and S, where we have 3 pluses and 1 minus. And the minus can be very big. So a priori, it's not obvious that there are a finite number of solutions to the tadpole equation. So you have to check that. So in some work with Mike Douglas and some work with Vladimir Rosenhaus, who is here in the audience, who can tell you more about this if you want to hear more after my 3-minute anecdote. We developed, first of all, we proved that there are a finite number of models, which is kind of the main point I want to make, which is that in 4 dimensions, it is not at all clear for various classes of vacuum constructions whether you have finite sets of constructions or not. In this case, it turns out that there are a finite number of models. And in fact, we developed some algorithms for going through all those models. So before it was known that there were a finite number, a similar group, Blumenhagen and Florian-Gemeiner and some others, did a systematic analysis of much of the space, or of a large number of models in this class over here, by basically tuning the moduli, and then for given values of the moduli, right, we have some SUSY condition. We have some SUSY condition, like these batteries have died again. Okay, have a SUSY condition like the one here. They plugged in the moduli and then found all solutions for given values of the moduli and scanned some vast number of things over a year-long computer search. And we're looking in particular for models with a certain SU3 cross SU2 cross U1 structure. So based on these kinds of algorithms, but they didn't know how big the space was, so they just stopped at a certain point. They went out to certain moduli, and then they said, okay, it looks like there's not much more there. We'll stop. We must have gotten almost everything. So Vladimir wrote some nice computer programs based on the algorithms we developed, which actually did a complete scan for SU3 cross SU2 cross U1 models. And we found some 13.4 million of them. And the interesting thing about this was that most of them were outside the range that Blumenhagen-Gemeiner et al. Had searched for. So we term this sort of the diversity is in the tail of the distribution. Basically, they looked at most of the possible models by their definition of the models, but the moduli they were looking at were such that for a given SU3 cross SU2 cross U1, there were lots of hidden sectors that you could throw in, and those were each appearing as different models. In the models that were scanned by Vladimir's code, using these algorithms we developed, there were lots of SU3 cross SU2s cross U1 with very constrained possible hidden sectors. And those dominated the set of possible models. So for instance, there had been a few such models found in the literature which did not get hit by the scan of the German group. And those, although they're uncharacteristic for models as a whole, they represent this diversity that's in the tail of the distribution. So that's the little anecdote. I'm sure Vladimir will be delighted to tell you more about it if you ask him. But with that, I'm going to stop for now. And then this afternoon, what I'll do is I'll do 60 heterotic vacua and 60 F theory. But any questions before we? Yes, please. Sure. We did somewhat, but we didn't go in full detail. There's a couple of technical issues. I think we might have even talked about this once when I was at Penn. But we looked at some aspects of the spectrum. But we looked at numbers of generations of certain things. But we don't have a complete.
So there's not it's not complete.
I'm not sure what use the list of numbers is there. But we have some information. If you want, we can talk with Vladimir about what numbers we actually have. But we have some information. I'm not sure we have enough to address what question you might have, but let's talk. Other questions? Okay. See you this afternoon.